In this example problem, we have a series circuit with a 50-volt power supply connected to 3 resistors. We know the voltage of the power supply is 50 volts. We know each resistance. So what we're going to do here, if you take a look, I have a table here on the right. And this table is pretty standard when I'm solving series circuits, parallel circuits, combination circuits, really all sorts of different circuits where I just list the different voltages, the currents, and the resistances, and then the totals as well. So if I just fill in what I know the total voltage is going to be 50 volts because that's my power supply. I also know that of my 3 resistors, I have 5 ohms, 20 ohms, and 50 ohms. So I'm just going to write them in order. So 5 ohms, 20 ohms, and 50 ohms. And then the whole goal of solving this circuit is to find everything else that we're missing in the table. So we want to find the individual voltage drops, we want to find the individual currents, as well as the total current and then the total resistance. The total resistance is a pretty simple one to find. And that's because we have a series circuit, we can just add up the 3 resistances to find that total resistance. So 5 plus 20 plus 50 is 25 plus 50, 75 ohms. So I know that my total resistance in this circuit is 75 ohms. Now the next thing I can do, and if you notice the way that this table is set up, I have V, I, and R. It's because Ohm's law applies not only for the entire circuit, but it applies for every single element as well. So I set this up so that way the rows are just Ohm's law. So if you look at the top rows, the total voltage, total current, total resistance, since I know the total voltage and I know the total resistance, I can just use Ohm's law. So I know that VT, the total voltage, is equal to the total current times the total resistance. And so if I just plug in the values that I have, I can solve for my total current. So if I just divide both sides by 75 ohms, I have a total current, so 50 divided by 75 is 2/3. I'm just going to keep it as a fraction for now, just to make it the most accurate as I possibly can. So I have a total current here of 2/3 of an amp. Now why that's helpful is because we know in a series circuit, the current remains the same throughout. And so since the current remains the same throughout, that means that all of my other currents are also 2/3 of an amp. So then the last step I have, if you take a look, I have the resistances and I have all the currents. I can find the individual voltages, again, using Ohm's law. So just 5 times 2/3, 20 times 2/3, 50 times 2/3, and that will give me all of these different voltages. So if I multiply 5 by 2/3, I end up with 3 1/3 volts. So that's the potential difference that we have across this resistor. So 3 1/3 volts. Then if I look at the next one, so 20 times 2/3, I end up with 13 1/3 volts. And then for the last one, 50 times 2/3, I have 33 1/3 volts. And so if you notice that the last rule does hold true, 33 1/3 plus 13 1/3 plus 3 1/3 volts, those all add up to the total voltage, that's 50 volts. And that's something else that I do. Not only do I go through and make sure that everything adds up in terms of the resistance and that the current's the same, but I also, even though the table's complete, I double check my answer just to make sure that the 3 individual voltages do add up to that total. And that is the case, so we know that this is the correct answer for this problem.